This is lesson 4 in the thermal physics topic. This is on specific heat capacity. You would have done a lot of this at GCSE, but this will be a quick recap to start with, and then the extra A-level stuff. So first off, we've got our exam definition of specific heat capacity. It's the energy required per unit mass to change the temperature by 1 degree Kelvin. That's the equation you normally see for it, and that's the equation you would have done at GCSE as well, is the energy inputted will equal the mass of the object times the specific heat capacity of the object times the change in temperature of the object. As you put in energy to something, it will change temperature. Now note that this equation only works when something does not change state. If you remember from the internal energy lesson, when something changes state, it doesn't change temperature, even though you give it energy. And that's a different equation we're going to use called latent heat, which we'll look at next time. We can rearrange this equation to make it specific heat capacity equals, so C equals E over M times delta theta, delta meaning change, theta meaning temperature. These are some specific heat capacity calculation questions for you. Can you just pause the video now and check that you can do them? So pause the video now. Okay, and now the answers will appear. Just make sure you're getting these right. Answers are there for you. A bit more of a challenging question for you now, if you got those right. So observe this. Here I'm using a hammer and I'm hitting a metal rod and I'm doing it for 10 seconds. So the kinetic energy of the hammer is being transferred into thermal energy of the rod, and then the rod is so hot that when it touches the matches, it actually ignites the matches. So kinetic energy of the hammer is being transferred into thermal energy into the rod. It increases the temperature of the rod, which is hot enough to ignite the matches. So if we read this now, I've got a 1.5 kilogram hammer traveling at 15 meters per second every time it hits the iron rod, and after striking it, it bounces back at 5 meters per second. So you can see the hammer has lost some kinetic energy. Its kinetic energy before it hit it was a half times 1.5 times 15 squared. Its kinetic energy after it hit it was a half times 1.5 times 5 squared. So work out the change in kinetic energy. That will be the thermal energy it gives to the rod on each collision. The hammer hits the iron rod 15 times, however. So how much total thermal energy does the rod gain? And then by knowing that the rod has a mass of 50 grams and a specific heat capacity of 420 joules per kilogram per Kelvin, if its starting temperature is 20 degrees Celsius, what was its ending temperature? So with your calculator, your pen and your paper, can you now work out the answer to that question? Just pause the video and work out your answer. A challenge for you to list all the assumptions you made, and the answer should be 127 degrees Celsius. So this is where we get into the A-level side of specific heat capacity a bit more. And here I'm looking at mixing materials together. So what I've got here is a picture of just a bit of water and then a scalding hot, incredibly high temperature copper ball. If I was to drop that copper ball into that water, the copper ball would get colder, it would lose thermal energy, and the water would get hotter, it would gain thermal energy. So they would eventually reach thermal equilibrium with each other, which is where they're at the same temperature. And to do that, the hotter object would cool down, and the colder object, the water, would heat up. The hot object is losing the thermal energy, and the cold object is gaining the thermal energy. And we can think of it as the change in energy of the hot object is equal to the negative of the change in energy of the cold object. The energy this loses is equal to the energy this gains. So let's have a look at this as a question now. So in that example, I've got a hot copper ball, and that hot copper ball is 700 degrees Celsius. The water has got a mass of 700 grams, and the water is at 20 degrees Celsius. So you can see the copper ball is much hotter. The ball is dropped in, and after some time, they reach thermal equilibrium at 80 degrees Celsius. That means that both the copper ball is now gone down to 80 degrees Celsius, and the water has gone up to 80 degrees Celsius. The specific heat capacity of the water is 4,200, and the specific heat capacity of the copper is 385. What is the mass of the copper? If you want to try it on your own, you can pause the video now, or you can watch me work it out first, and then I'll have another example for you to try yourselves. So here I'm writing down everything I know. I've got the mass of the water, I've got the change in energy of the water is 80 degrees Celsius, the heat capacity of the water, the change in temperature, I forgot to do my theta there, the change in temperature of my copper is 620 degrees Celsius because it goes from 70 down to 80, and the specific heat capacity of my copper. What I can say is that the energy gained by the water is equal to the energy lost by the copper. So writing out the full specific heat capacity equation on both sides, I get the mass of the water times the heat capacity of the water times the change in temperature of the water is equal to the mass of the copper times the heat capacity of the copper times the change in temperature of the copper. I want to know the mass of the copper ball, so I'm going to rearrange this equation now for MC. The mass of the copper ball is equal to that. And then what I'm going to do is I'm going to just fill in everything I know. I should know all of these values here, so I'm going to fill those in now. And you should get an answer of 0.074 kilograms. So make sure you've got that filled out in your notes. That's a worked example for you, and you can come back to that when you do the Isaac physics questions and when you do the next questions in this video. So this is another question for you to try on your own now. Read it through. I've got a 1 kilogram block of iron at 600 degrees Celsius placed in good thermal contact, which just means they're eventually going to reach thermal equilibrium. So my 1 kilogram block of iron at 600 degrees Celsius is placed in contact with a 20 degrees Celsius block of copper of mass 1 kilogram. So same mass, different starting temperatures. Assuming no heat is transferred to the surroundings, so we only transfer heat and energy between the two blocks, what is the temperature of both blocks when they reach thermal equilibrium? So this is a tougher question now, a much tougher question. Imagine I've got a block of iron and a block of copper. This time you want to work out what the final temperature is. The final temperature of both will be the same temperature. Can you work out what that will be? So pause the video now and give that a go. That is a tougher question than the previous one. Okay, the answer is 323 degrees Celsius. Apologies for my O there, that should be risen. 323 degrees Celsius. Well done if you got that. So how can we measure specific heat capacity in the first place? Well, what I can do is I can get my solid object, my block of metal it might be, I can heat it up by applying energy to it using an electric heater, measure the change in temperature of it, measure the mass of it, and then I use the equation. And this is what your circuit might look like with your heater in it. And if you know the current, the voltage, and the time that you're connecting it in the circuit for, that current is flowing through it for, you can use energy equals IVT. This is going to be a PAG when we come back. So knowing how to do that practical is going to be really useful. Knowing what equations we need to use, knowing what equipment we're going to be using, and what equipment will ensure that we are accurate in our measurements are all going to be really useful to being successful in that practical. Finally, we're going to look at constant volume flow heating. So this is where you've got a constant volume or a constant mass of fluid, in this case of water, flowing through a heater, and it heats up the liquid. This is a really important concept in engineering. It's something that comes up in so many uses. You think of hot water in your homes, cars, in power stations, and they often use it to cool things down as well. It can be used in reverse. So what we're going to do is we're going to take this equation, our specific heat capacity equation, and we're going to divide both sides by T. And that's going to give us E divided by T is, you might remember, power. And this side divided by T will give us mass over T times specific heat capacity times change in temperature. So here we have got the power of the heater equals the mass flow rate. This term here is called the mass flow rate. The rate of flow of the mass times the specific heat capacity of the fluid times the change in temperature of the fluid. So as a question to try, can you calculate the power of an industrial heater when there is a mass flow rate of 1.20 kilograms per second that heats water from 10 degrees Celsius to 80 degrees Celsius? And the specific heat capacity of water is 4,200. So just pause the video now and give that question a go. and you should have got a power to the nearest two significant figures of 350,000 watts. 350,000 watts.